Welcome to the second lecture. First, we'll cover just some logistics. So homework 1 will be posted today, and it's going to be due Monday, October 7th, and we'll cover actually some of the topics that will be in homework 1 today. So pay attention if you want to be able to do homework 1. Fill out preferences for papers by tomorrow so that we can start assigning papers to you. We'll assign papers as quickly as possible, especially for the first group that's presenting on Thursday next week. Also, a reminder that the TensorFlow review session is tomorrow at 4:30 p.m. in Gates B03. That's going to be led by, and then I guess lastly, for enrollment, if you filled out the form and have not received a permission code, then at this point, unless you filled out the code like a minute ago, I think we've handled basically all of the cases. So just send the staff an email or a post on Piazza asking about that, and we can look at that on a case-by-case basis. If you still haven't filled out the form, please do fill it out. Although at this point, maybe let us know if you fill it out because we may not be monitoring it quite as frequently. Okay. Any logistical questions before we, yeah? The homework will be due midnight on Monday, October 7th. And the date will also be posted, the time and date will be posted on the assignment. Okay, great. So the plan for today, we actually have a lot of material to cover. So first we'll be talking about some of the basics of multitask learning, things like the types of models and architectures that these algorithms typically use, as well as how we actually go about the training process for multitask learning, some of the challenges that arise when you try to train across multiple tasks, and a case study of actually trying to use multitask learning in a real-world application, and some of the challenges that come up and some of the results that were there. Then we'll have a short break, around like 2 minutes or so, and then we'll be covering some topics, some kind of basic topics in meta-learning. We'll get into more advanced topics in future lectures. This will include things like the meta-learning problem formulation, a general recipe of meta-learning algorithms, and kind of how you go about building these types of algorithms. And then lastly, we'll talk about a specific class of meta-learning algorithms called, that I'm going to refer to as black box adaptation approaches. And these last two things, actually how you go about setting up a meta-learning algorithm and implementing a simple approach to meta-learning will be the topic of homework 1. Okay, so let's get started with multitask learning. So, and actually, before we even get into multitask learning, let's look at some notation. So say we have some neural network. The neural network is going to take in some input x and produce some output y. And the input might be something like a picture, and maybe the output is the class corresponding to that picture, the class of the animal, for example. Another example of an input might be like the title of a paper, for example. Maybe you're trying to decide which papers to read or which papers that you want to review, and then you kind of want to decide whether or not the paper is going to be too long or not. This is essentially a variety of classification type problems you might imagine. The weights of the network will use theta to denote the weights, and then you can basically view this neural network as producing a distribution over outputs y given the input x. Of course, this could also be a deterministic function. Viewing it as a distribution is a generalization of a deterministic function. Okay, so in single task learning, the way that this would mostly be review for all of you. So single task learning, at least a supervised single task learning problem, we assume some data set where we have input-output pairs. And we probably have many input-output pairs corresponding to that data set. And our goal is to minimize some loss function that is a function of the parameters and the data set. We want to minimize that loss function with respect to the parameters. And so one typical loss function that we may use is something that looks like negative log likelihood. So our loss function is going to correspond to the expectation of the data points in our data set of the log probability of our predictions, the log probability of the labels under our neural network predictor given the input. Okay, so this is kind of standard single task learning. The way that you would typically optimize this log likelihood is by backpropagating into the parameters of the network and running something like SGD or your favorite optimizer, Atom, Attograd, Momentum, whatever. Okay. So now what do we actually call a task? We talked about this a little bit last time on Monday, and we'll try to talk about this a little bit more formally this time. So the way that we're going to define a task for the sake of basically the first half of this course before we get to reinforcement learning is something that looks like this, where we're going to have some distribution over our inputs, a distribution over the labels given the inputs, and a loss function. And essentially these two distributions P are going to correspond to the true data generating distributions. And so of course we don't actually have access to these data generating distributions, but it allows us to kind of reason about what we're going to be seeing at training and test time. In particular, what we're going to be seeing, the kind of things that we will have access to is we'll have a training set and a test set for each task. And we'll assume that each of these distributions are drawn from the same data generating distribution P, or PI. So essentially, what a different task corresponds to, different tasks may vary based off of the input distribution, the label distribution given the input, or the loss function. Okay. One notational note is that in future slides, I'll be using DI as shorthand for the training data set. And yeah, we'll get to that in a couple minutes. Any questions on kind of the basic setup? Yeah.
What's the triangle over the equal sign?
Oh, that just means that we're defining the task to be equal to the thing on the right. Okay. So this is our task. And for each task, we have corresponding data sets sampled from some distribution. And let's look at kind of some examples of what different tasks may be. In particular, what different sets of tasks may be, what kind of different problems they correspond to. So for example, we may have a multitask classification problem where we want to be able to perform different classification tasks. And in this case, the loss function will be the same across all of the tasks. The loss function will be something like cross-entropy loss for all of the tasks. But the inputs, like the images that you're seeing for each task or the labels corresponding to those inputs may vary across different tasks. For example, maybe different tasks correspond to writing, to be able to recognize handwriting digits on a per language basis. Maybe you want to, like one task is to be able to recognize characters corresponding to Braille, for example, while another corresponds to another language. Another multitask classification task might be like a personalized spam filter. The emails that I get are probably very different than the emails that a high schooler gets, for example, or like a professional athlete, for example, and so the types of spam will be different. So classifying spam for one person could be one task, and classifying spam for another person could be a different task. In that case, the loss function is the same across all tasks. The P of X is different because the types of emails that each person will be receiving, the distribution over emails will be different, so you'll have a different PI of X for each person. And also, different things might be, one thing that might be spam for one person might not be spam for the other person, and so you may have a different PI of Y given X. Okay. So that's one example. Another example of a multitask learning problem is what's called multi-label learning. In this case, the loss function and the distribution over the inputs is going to be the same across tasks. And what's going to be different is you're going to want to be able to make predictions, basically be able to predict different labels, perform different kind of output tasks given your input image. So one example of this is attribute recognition. So if you have a data set of faces in the Celeb data set, for example, one task might correspond to detecting whether or not the person is wearing a hat. Another one might correspond to detecting their hair color, things like that. So their P of X is the same, the loss function is the same, but Y given X is different because you have different binary classification tasks. Another example is something like scene understanding, where maybe given an image, you want to be able to predict the depth of that image, the different key points, the surface normals of that image as well. So this is a common problem in computer vision. So both of these examples were settings where the loss function was actually consistent across all tasks, and what was varying was the data distribution. And so what are settings where the loss function might vary across the tasks? So One setting is maybe one of your tasks corresponds to predicting a discrete variable, whereas another one corresponds to predicting a continuous variable. In that case, maybe one task might have like a cross entropy loss function, whereas another might correspond to mean squared error, or something more sophisticated than that, a different way to represent likelihood, essentially. Another setting where it might vary is actually if you care more about one task than another task. Maybe you care more about accurately predicting the surface normals than about the depth, for example. Then you might kind of increase have a loss function weight corresponding to one task that's higher than the weight of another task. Okay, so here are some examples of kind of different multitask classification or different multitask learning problems that we might want to solve. How do you actually go about solving them? So we can go back to our neural network, and if we want our neural network to do multiple different things, then we need to tell it what it should do. And so in some ways, we need to condition on the task in some way. And so what we're going to have is we're going to have some task descriptor z, and we're going to pass this task descriptor into the neural network in some way. And so I'm just going to draw an arrow towards the neural network to indicate that, and in a minute, we'll talk about different ways that we can condition on that task descriptor. And of course, now our neural network is not going to be just a function of x, but it's also going to be a function of this task descriptor zi. Okay, so for example, in this case, maybe x, we can go back to the paper title example, maybe x corresponds to paper titles, and now instead of, oh, it's back, okay. So maybe instead of trying to figure out what paper you want to read, you now need to review the paper and produce a review for a conference, and maybe you're a bit lazy, so you ask your neural network to predict a summary of the paper for you so that you can then base your review on the summary. Or maybe you're even lazier and you just want it to output the paper review directly. Hopefully these aren't the reviewers for your papers, but yeah. Okay, so what is this task descriptor thing? The simplest example of what this task descriptor might be is just a one-hot encoding of the task index, just a vector that tells you if it's task 1, task 2, task 3, etc. This is just kind of an index corresponding to the task. But more generally, it could also be whatever metadata that you have about that task. If your task corresponds to personalization, then the task descriptor might include information about that person or that user. If it's something, maybe you have kind of a language description of the task you want to perform, so you can provide that language description to the network. Or maybe you have some formal specification of the task, like maybe you're trying to design circuits like was mentioned on Monday, then you might have kind of a formal specification of the type of circuits that you might want your neural network to be producing. Okay, so this is the task descriptor, and then our objective now becomes basically the same as what it was before, but now we're going to be summing over all of the tasks that we have. Okay. So this is the basic setup. Now we have a couple design decisions to make. So we have a model and we have an objective. And so we have a decision for both of them. The first is how should we design the model? And the second is how should we optimize the objective? So particularly the big decision that we have to make in multitask learning is how do we condition on this task descriptor zi? And the algorithm decision, like I mentioned, is how do we optimize our objective? So let's first talk about this, this first question. So this is all about conditioning on the task. Let's assume that zi for now is just going to be the task index, like a one-hot encoding of our task index. And we only know kind of information about our task is this index, basically. So I have a question for you, which is, how should you condition on zi in order to share as little as possible between the tasks in your neural network model? Essentially, how should you structure your neural network model such that it shares basically as little as possible between the different tasks? Yeah?
Then we have separate networks for each task, basically, then do this entirely separate.
Yeah, exactly. So what you can do is you can have separate networks for each task where you have each of them have completely separate weights. And then the way that you condition on your task descriptor is you pick the corresponding task, which corresponds to this sort of multiplicative gating where you're just selecting which of the outputs you're going to produce based off of your task index. This is basically a complicated way to say that we're just going to be training independent networks, and it's kind of one way to represent independent networks within a single model, essentially. Okay. So we get independent training within a single neural network, and there's no shared parameters across tasks. Now, what about the other extreme? So the other extreme would be something like this, where we take our neural network and we just concatenate the task index somewhere, either at the activations or at the input, and then train the network as normal. And in this case, all of the parameters are shared, except for one tiny part of the parameter vector. What is the kind of tiny part of the parameters that's not shared? Sorry, repeat that?
The one that will be multiplied with the indicator.
Yeah, exactly. So basically the weights that are right after this zi, if you have a fully connected layer right after zi concatenated with your features, the part of that matrix that corresponds to, that is basically right after zi, will have basically different components that are not shared for each of the tasks. Other than that half of that matrix, all the other parameters are shared. Yeah?
This also kind of forces all the inputs to have the same size or mass.
Yeah. Yeah, exactly. So in this case, we assume that all the inputs have the same size, the same dimensions. One thing that you could do is if different tasks have different sizes, you can basically you can have some sort of recurrent neural network or some sort of attention-based model that basically aggregates over the variable dimension. Like if one of them is time, for example, it aggregates over that. Whereas maybe some tasks are text and another is images. And in that case, you would probably want to have different first parts of that network to take in those different modalities of data. And we'll see an explicit example of how that has been done in the past. Yeah.
So I'm a little unclear as to how the parts for after zi do not end up sharing weights, because I can imagine that if zi is just a one-hot encoding, the weights to the right of that one would just be tuned in such a way that it will respond to only specific types of zi. So wouldn't they essentially be sharing all the weights on the right side?
So this is a good question, and it's a fairly nuanced point. So basically, each you can view a fully connected layer corresponding to a weight matrix times a vector, and when you take the top part of that matrix will correspond to, or sorry, the left rows of that, the left columns of that matrix will correspond to the features, and the right columns of that will correspond to the task vector that's being passed in his input. And if zi is a one-hot vector, then you'll have one entry in that matrix that is 1, and the other entries in that vector will be 0. And so basically all of the ones where all of the columns that have an entry in zi that corresponds to 0 will be zeroed out and won't be used for that task, whereas the columns that have the 1 will be used for that task. Yeah?
Would still share all the parameters, just that when the activations are computed, you're only computing parts of the weight matrix as opposed to the whole thing.
Technically, although if you kind of mathematically go through the gradients for those columns will be 0 for the tasks in which the input is 0. Yeah.
So essentially, it's just zi specific, depending on the type of encoding you decide to use.
Yeah, exactly. So if zi was not a one-hot vector, for example, then you would have that part of the matrix would be shared parameters. Another kind of somewhat interesting fact about this is if you concatenate zi at every single layer of the network, you'll have more task-specific parameters, whereas if you condition it only on a single layer of the network, you'll only have kind of one set of task-specific parameters. Yeah?
So you're sort of implicitly doing it as an embedding layer, in fact, if you're making zi one-hot.
Yeah, exactly. So the output of that part of the matrix is a linear transform on the one-hot, which produces a vector. Basically, the column of that matrix corresponds to the resulting vector, which you could view as essentially as an embedding, a linear embedding of that task. Yeah.
So my understanding of how neural networks learn to solve a task is through updates of weights, right? But if you have the zi being input only one layer versus multiple layers, in any case, it doesn't really affect the weights. Or could you go into a little more detail of what kind of differences those make in terms of the network's expressibility and able to solve these tasks? Because they're not really affecting the weights per se.
Yeah, so if you add ZI to every layer, then you're increasing the number of parameters per layer, of course, and you're also, like, the parameters that you're adding are all tasks, well, they're not all task specific, they're mostly task specific. Maybe like it depends on the dimensionality of each vector. It's somewhere around half of the new parameters are task specific and half of the parameters are shared. So as you add weights to neural networks, they become more expressive. As you add task-specific weights, then in some ways they become even more expressive because for different tasks, they can represent completely different things.
So then why would you opt for having fewer of those inputs as opposed to more?
We'll get to that in a second. Yeah. Okay. So we've been talking a lot about shared parameters and task-specific parameters. And one kind of alternative view on the multitask learning problem is that you can split your parameter vector into these shared parameters and task-specific parameters, which I'll denote as theta sh and theta I. And then if you view kind of that as your parameter vector, then your objective looks something like this, which is basically exactly the same as the previous objective. But it decomposes and makes it obvious that the task-specific parameters are only optimized with respect to the objective for that task. Whereas the shared parameters are optimized over for all I, basically, optimized over all tasks. So one of the things that's somewhat interesting to note, based on both of the examples that we saw, the multiplicative gating example as well as the concatenation example, is that choosing how you condition on Z in many ways is equivalent to choosing how and where to share parameters. Yeah. So essentially, the choosing how to condition on Z corresponds to thinking about this sort of optimization problem and thinking about where those shared parameters should lie and where those task-specific parameters should lie. Okay, so let's go over a few more choices for how we might go about conditioning things. So we saw how we could do concatenation-based conditioning, where we basically take that task descriptor and concatenate it with the features, and then do a linear layer after that. Another option to concatenation-based conditioning is to add the task vector to your hidden units, to your features, where you basically have a linear layer to make sure that such that you can basically add it on such that it's the same dimensionality, because the dimensionality of ZI may not be the dimensionality of your features. You run it through that linear layer and then add it. Interestingly, I presented both of these as two different options, but they're actually just the same thing. So you can essentially view additive and concatenation-based conditioning as the same. So for example, on the left side of this figure, you see that you're concatenating X and Z, and then you have this weight matrix that corresponds to the kind of the weights that are applied to each of those layers. And you can view that as you kind of apply the matrix multiplied to those two parts of the vector, you basically get these two components that are added together, which illustrates how basically the right-hand side of this figure corresponds to the additive conditioning, which is equal to the left-hand side, which is concatenation-based conditioning. Okay, yeah?
In all of this, we're assuming that Z is a one-part vector.
Yeah, so this is assuming that Z is a one-hot vector.
Right, but which is basically saying all of your tasks are independent of each other in some way. But if I represent tasks as a vector, where two similar tasks have similar vector representations, and I feed that in, then I could share all the parameters, right?
Yeah, absolutely. So if you have more information about how tasks are similar or dissimilar from one another, then you can feed that into your network as opposed to ZI. Interestingly, determining how similar two tasks are to each other is actually a big part of the multitask learning problem itself, is kind of determining how you should be sharing content, sharing parameters, sharing structure across these different tasks. And in many multitask problems, you don't necessarily have that a priori. But there are certainly many examples, and we'll actually see a practical example where you do have some information about the task, and you can use that to condition your network on in a different way. Okay. A couple other very common conditioning choices. This is again for the one-hot case where you don't have a lot of information about how two tasks are shared. One is kind of this form of multitask or multi-head architecture where you have some set of parameters and then you split off the network into different heads. The citation here is for 2017. That's just for the visual. This has been something that people have used for a long time. And then one other interesting choice, or one other kind of very common choice that you can do is multiplicative conditioning, which is basically identical to additive conditioning, except instead of adding, you multiply. So you project your task matrix, your task vector onto a vector, and then you multiply that onto your onto the activations either in the input or at kind of intermediate representations of your neural network. Okay, so why might this sort of multiplicative conditioning be a good idea? There's actually a few different reasons. So one is it's more expressive than additive conditioning. You can represent multiplicative interactions, whereas with additive things, you can it's much harder essentially. And the other reason is if you think about something like multiplicative gating that we talked about before, this sort of gating is something that can very naturally be represented by multiplicative conditioning. And not just multiplicative gating, but also things like a multi-head architecture, where you want to basically be choosing which parts of the network should be used for different tasks. So essentially, this sort of multiplicative conditioning, where you're multiplying this embedding onto your activations, allows it to modulate different features, such that you can completely turn off features. You can completely only use some heads for one task, only use some parts of the network for one task versus another task. Yeah. That's a good question. I would say it's a very simple form of attention mechanism. I think attention mechanisms usually involve dot products. And in this case, you're not actually summing across the dimensions. You're just doing an element-wise multiplication. Yeah?
Are there different permutations of multi-head architectures where you could split into task dependence at different stages and then back into shared layers? Or is that just not, does that not work?
Yeah, you can definitely do that. And we'll see an example of that in the case study, actually. And multiplicative conditioning allows you to do that, and allows it to actually learn how to do that in a completely automatic way. Yeah?
Is that literally just a Hadamard product? Because it seems like
yeah.
Just a Hadamard product, it wouldn't be as expressive as the previous architectures you showed.
As expressive as the additive,
or yeah, an additive with another linear layer or something like that that would actually use the input.
Right. So these diagrams have been kind of looking at a single layer at a time. Of course, when you add kind of layers, a neural network is a universal function approximator, and so if you concatenate two things and then want it to give you the product, a neural network can represent that function. And so technically, the additive function, the neural network can also represent this when you concatenate. It's just in practice. And so technically, all of these are kind of all universal function approximators for in the multitask setting. In many ways, it's kind of more about what you're readily allowing the network to do and how kind of the optimization process itself, although it's much harder to say things about optimization than about the types of things that like an individual layer can represent, for example. Yeah?
Do any of these architectures allow for executing of tasks that you haven't like specified will be a task that you'll execute on before training?
Can you repeat the question?
Like, if you have to know a priori, like the number that you only train on, you only like ever do tasks A, B, and C. Are there methods in which you can actually use the train model for task D?
A task D that you haven't seen any training data for? So yes, so that's a good question. In that case, if you want to be able to generalize to an entirely new task that you haven't seen during training, you'll need something other than a one-hot vector. Because if you only have a one-hot vector, then you don't know how that new task relates to anything that you've done before. But if you have a language description, for example, then then in principle, these models could learn how to generalize from basically given a new language description to perform that task, given enough data of other language descriptions that share commonalities with what you're seeing at test time. And then in the second part of this lecture, we'll be talking about how we can quickly learn new tasks from data by using experience on tasks on previously seen tasks. Okay. There are also more complex choices that we can go with as well. So here are some architectures from the literature, for example. These things include various modules, various attention components, different gating mechanisms. We don't have time to go through all of the possible choices that you could do here. Although some of I think one or two of the readings that we'll have will cover a couple different options there. Yeah, so the main takeaway though that I'd like to give is that there are, well, I guess one, there are a lot of different choices we have to make when choosing the architecture. And unfortunately, these design decisions are basically kind of correspond to neural network architecture tuning in that they are problem dependent. So one architecture will work well on one problem, but won't necessarily work well on another problem or another set of tasks. In many ways are largely guided by intuition or knowledge of the problem. So if you know that two tasks are similar, you might have them share more, whereas if you know that two tasks are different, you might have them share less. And I would say that currently it's in some ways more of an art than a science. And there isn't kind of like any guide that can tell you exactly how to do this, given a new set of tasks that you want to be able to learn. But hopefully, this is a very active area of research, and hopefully in the kind of coming years, we'll have a better idea for how to do this. Okay. So now that we've talked about the model architecture a lot, what about actually optimizing this objective? In many ways, this is fairly straightforward compared to standard neural network training. Kind of a very basic version of optimizing this objective would correspond to first sampling a mini batch of tasks. So we have different tasks, we need to sample different tasks and then sample data points for each task. So unlike the standard supervised setting, we won't just be sampling once, we'll be sampling twice. Then we're going to compute our loss function on our mini batch by kind of measuring a stochastic, basically kind of getting a stochastic gradient rather than the true gradient, because we can't evaluate the gradient on our entire data set. We backpropagate the loss to compute the gradient, and then apply the gradient to your parameters using your favorite neural network optimizer. So basically this is the same as standard single task learning, except that we're going to be sampling a batch of tasks and a batch of data points for each of those tasks. And note that kind of these first two steps ensure that the tasks are sampled uniformly, regardless of data quantity. So if you have one task that has a lot more data than another task, then this will ensure that you're sampling them at equal rates, which is what we're optimizing for on the top. If you care more about the task that has more data, then of course it makes sense to weight those differently and sample at different proportions as well. Okay, and one other tip here is that if your different tasks correspond to regression problems, this isn't really necessarily specific to the optimization algorithm, but it's pretty important to make sure your task labels are on the same scale. Otherwise, inherently, your loss function is going to have a greater scale for which the labels have a greater magnitude. Okay, so now that we've gone over kind of the basics of the architectures and the challenges, or the architectures and the algorithms, let's talk about some of the challenges that come up. So in many ways, the kind of number one challenge that I view with multitask learning is the problem of negative transfer. And this kind of the symptom of this is when, like, if you train independent networks and that's doing better than your multitask learning method, then that means that you're getting negative transfer. It means that the kind of data and training from one task is adversely affecting the training of the other tasks. So for example, and this is actually a problem that is quite prevalent, and in some cases maybe you care more about computational efficiency and it's not practical to train independent networks. But for example, we were actually recently trying to write a paper on multitask learning. There's this common multitask version of the CFAR data set where you break it down into different tasks corresponding to the different kind of upper level categories of CFAR. And we kind of evaluated all the multiple state-of-the-art approaches for multitask learning and got various levels of accuracy on this data set. And then we trained independent networks, and it was performing better than kind of all of the recent papers. So why does this happen? Why does negative transfer, why aren't we actually getting benefit from training across multiple tasks? One is optimization challenges. So if basically gradients of one task are interfering with the training of another task, basically when you compute gradient for task 1, compute gradient for task 2. If gradient 1 hurts the weights for task 2, then the optimization will be more difficult. And also tasks may learn at different rates. So if one task is learning a lot faster than another task, you might end up learning one task very quickly, and then it might get stuck trying to learn task 2 because it's kind of already learned something and it doesn't want to learn something else. Essentially, kind of the optimization gets stuck because it's kind of in this local optimum. Okay, and the other issue that you might run into is maybe you have limited representational capacity. So multitask networks in general often need to be much larger than single task networks. This is very intuitive, but it can be easy to forget. And in this case, if it isn't as large as it needs to be, then you're going to see underfitting. And that's a kind of a symptom of limited representational capacity. Yeah.
With respect to optimization challenges and multitask learning, how do you incorporate? So, I mean, this case is probably because there's balanced data across all tasks. How do you deal with scenarios where one task might have I don't know, 5% of the samples that another task has? How do you leverage curriculum learning stuff to handle these types of scenarios?
Yeah, so that's a good question about basically how to handle optimization challenges, especially when one task has more data than another. One is kind of the thing that I mentioned before, is you sample the tasks and basically balance them such that they have the same amount of data, such that it doesn't favor one task over the other. Because oftentimes if you don't do that, then it will learn the task that has a lot of data and it won't learn the other one. People have explored curriculum learning techniques, and we'll talk a bit about that later on in this course. In general, I would say that the optimization challenges aren't completely well understood. We're still trying to understand kind of in general the single task optimization landscapes, let alone the multitask optimization landscapes. I do think, though, that there's been a lot, I'm actually pretty optimistic about being able to understand these sorts of challenges very soon. And we may even, later in the course, cover, try to get a better understanding of these optimization challenges and how to mitigate them. Yeah?
So I'm confused about how you actually define this negative transfer phenomenon because we don't have perfect overlap between the different tasks, otherwise they would be different. So when you have one network versus, say, 10 different networks stringing out different tasks, assuming that all of the training are perfect to the network's capacity, then you gotta have worse performance for the single network versus all 10 networks, right? Because there's extra information that maybe the network isn't going to be able to express. So you expect larger networks, but how do you compare if your network is larger?
So you're saying that you're not, why would you expect positive transfer? Why would you? Yeah, so one situation to expect positive transfer is when you don't have a lot of data per task. And so if the tasks are related enough, then the features learned for one task will be useful, or the representations learned for one task will be useful for the other task. So it's essentially a way to share data. And as I'll talk about in 2 slides, you can basically kind of, another way to view multitask learning is essentially a form of regularization. And if your kind of problem setting, if regularization would be helpful, basically, and more data would be helpful, then those are some of the settings where you would definitely expect positive transfer.
So it helps with generalization?
Generalization, essentially, yeah. In reinforcement learning, we'll see other benefits as well relating to exploration. Yeah?
So if all the tasks have exactly the same data, is it usually better to train independent networks?
That's a good question. So you mean all the same inputs, but different labels?
All of them have the same input, but I want to use the same input to predict different things.
Yeah, so in that case, you can definitely still see benefits from multitask learning. Essentially, each task has its own form of supervision. And when I was talking about data sharing, it's not necessarily actually about sharing inputs, it's about sharing supervision. And so if you have, basically each of those tasks correspond to different amounts of supervision, and those can be used for building more flexible representations, more powerful representations that can be used for better solving one of your tasks. Yeah.
So if you want to prevent transfer but still like maintain or leverage the representations you learned from one task, could you just do like a simple transfer learning where you just initialize your new net with those trained specifically for this task?
Yeah, you can definitely do that. In practice, fine-tuning, I'll talk a bit about fine-tuning next lecture. In practice, that makes fewer assumptions about the availability of data because you assume that you can't kind of access that first data set. And so in practice, many times, if you have both data sets available, you should use both of them, and you'll be able to get better performance. Yeah?
Is there a simple kind of like similarity metric that you could use before you do this kind of training, or do you just have to perform the optimization and see if it performs well, and that's a sort of measure of how much shared structure there is?
Yeah, that's a very good question. I don't think that this question is necessarily known. I think that there maybe are techniques where we could better get a sense for this before training. But my sense is that how similar two tasks are is intimately tied to how easy it is to learn them together. And so I guess the pessimistic side of me would answer that it's actually not possible to a priori know how much you should share ahead of time. But I think it is kind of the more optimistic side of me says that kind of the optimizers should be able to figure it out throughout, like in an online fashion throughout optimization during the learning process. So I don't think we can probably do it before learning, but I think it can happen during the learning process. Yeah.
Yeah, I want to understand better why a multitask network needs a larger network. So assuming we have the same network, but independently trained on different tasks, and it works okay, but altogether doesn't work okay. It seems to me that it might be just a problem of because they're sharing the same like activations and they cancel each other. Whereas a bigger network will just be the backpropagate gradients might be more sparse within the network, so they don't cancel as much.
Yeah, so it certainly could be that larger networks help because they alleviate optimization challenges. And people have observed in general in single task learning that if you have a larger network, they actually sometimes optimize faster than the smaller networks. But separate from optimization, there is also just the representational capacity of like, if you're doing a single task, that's one function. And if you're doing another task, assuming that task is different, the representational capacity needed to represent both of those functions is greater than just an individual function. But it may be that actually the optimization challenges potentially could even have a greater impact on this sort of observation. Yep?
So sometimes when we test machine learning algorithms, we sort of generate the data set where we know base error. So we know how well an algorithm in principle could do. Are there similar sort of toy problems in this setting where beforehand we actually know how much positive transfer is possible?
Not off the top of my head, but there certainly could be literature on that given the extent to which people have studied it. Yeah, feel free to like post that on Piazza or something, and we can try to find something.
To look for that together because it's a bit hard to even understand. Like, because then it would be more obvious to find some clear example. Yeah, here there will be transfer.
Yeah, I do suspect that we won't be able to find an example with real data or in real problems.
But I don't think you
yeah.
Generate data.
Yeah. Yeah, I think that would be interesting. Yeah?
be equivalent to like, in the ideal case, wouldn't that be equivalent to having a bunch of these different networks with the same number of parameters, since the multiplicative portion would be able to switch it to a completely different set of values?
In principle, yes, if you use that kind of multiplicative conditioning. So in principle, it does have the representational capacity to represent completely separate networks. And that actually is one of the good reasons to use that sort of gating. In practice, the optimizer might have challenge finding that solution. Yeah. And so it may not actually be able to find that solution, but technically it should have that capacity. And I guess one thing I will add to that is we actually have observed very recently that in many cases it's actually very challenging for the optimizer to find that solution in tasks where the things that you're learning are very distinct from one another. Yeah.
If we have, for example, like one neural network trained on one task and one trained on another task, is there a way to combine them so that it becomes a multitask network?
So you can combine them, but very naively and stupidly by just kind of using a task selector to pick which network you want to use. To my knowledge, there aren't any technique. Well,
maximize the overlap so you get some advantage.
I don't know of any. We'll cover this when we get to reinforcement learning. Yeah. So there are some techniques that do kind of take two trained networks for tasks and then try to learn a single network that fuses them in some way. Okay, I should probably get on to the next few slides. So the takeaway here is I don't even know if I've even said this yet, but I think all of you have inferred it, is that if you have negative transfer, you can share less across tasks, train a bigger network. And one of the interesting things here is actually sharing versus not sharing parameters is not just a binary decision. You can actually also do what's called soft parameter sharing. And so what this looks like, or one version of this, is where you have you can break down your objective, as I showed before, into shared parameters and task-specific parameters, and then basically add this term that encourages the task-specific parameters to be similar to one another. And you could do this at different layers of the network. You could do it for different pairs of tasks, for some pairs but not other pairs. You could also do it with respect to a single set of global parameters and tie them all to a single set of global parameters instead of doing this sort of pairwise loss. And so what this looks like is you have two separate networks, and what you do is you kind of softly constrain the weights to be similar to one another rather than actually having them represent the same exact value. So one of the benefits of this is it allows for more fluid degrees of parameter sharing, where if you set the weight on this loss, this right-hand loss to 0, then you have 0 parameter sharing. If you set it to be a very high value, such that essentially constraining the optimization to set them such that they're equal, then that corresponds to hard parameter sharing. The downside is that it's kind of yet another set of decisions and hyperparameters that you need to tune and make sense of when you're thinking about your algorithm. Okay, and so now that I've talked about negative transfer, another problem, which is in many ways somewhat orthogonal to this challenge, or kind of the opposite of this challenge, is the challenge of overfitting. And so if you observe that if you have only a small amount of data per task and you find yourself overfitting to those tasks, then it actually may be that you're not sharing enough. It may be that you just need more data, but it may be that if you shared more, that would act as a stronger form of regularization, and you may be able to overfit less. Okay, so now I want to go into kind of a case study of actually applying these sorts of multitask learning algorithms in practice. And so this was actually a very recent paper that came out in the past 2 months, and they were looking at making recommendations to users for YouTube. And this team is from Google, and to my knowledge, this is some of kind of what we'll be covering here are some of the decisions that they have made when actually making recommendations to users. Yeah, so here's an example. You have, you're kind of watching this, this lecture on deep learning, and then on the right, you might be getting some recommendations about what video to watch next. So there are a couple challenges that come up in this sort of problem, and the way that they formulate it as a multitask problem is making predictions about user engagement and about user satisfaction. So you essentially have these conflicting objectives to think about: should I generate a video that a user will rate highly? Can I predict whether or not the users will share that, whether or not they'll watch that video? And the types of things that you share are not necessarily the types of things that you would watch for a long period of time, for example. The second challenge that comes up that I won't have a lot of time to talk about today, but is also a bit interesting, is that in these sorts of recommendation systems, you also have a form of feedback loop where users may have watched something simply because you recommended it, and this leads to bias in your data. And so they also have an interesting technique that they use to address this bias. And if you want to kind of find out more information about that, you can look at the paper. Okay, so how do they actually set up this problem in this framework? So the input is what the user is currently watching, which is called the query video. And they also know some features for that user. And then what they do is they first generate a few hundred candidate videos that they might think that user might want to watch. They then rank the candidates, and then they serve the top ranking videos to the user in that recommendations bar on the right. The candidate videos, this wasn't really the main focus of the paper, but the way that they do this is they pull videos from multiple candidate generation algorithms. These algorithms do things like try to match topics of the video that you're currently watching. They also try to look at the videos that are most frequently watched together with the video that you're currently watching, as well as a number of other forms of metrics. And then kind of the central topic of this paper was, given a large number of candidate videos, can you figure out basically rank those candidates into an ordered list where the top things correspond to the ones that you actually want to serve? Okay, so how do you actually formulate the ranking problem? What this looks like, again, similar to before, your input is going to consist of the query video and features of the user. It's also going to the input is also going to be one of the candidate videos, so this is going to be operating on each of the candidate videos. And interestingly, in this case, things like the query video and the candidate video, these aren't actually literally the videos. They correspond to information about those videos, like features of the video, such as the topic, the title, the upload time, and then also user features like user and context features such as their user profile, the time of day, and a variety of other things. So this includes both textual data as well as non-textual data that they use a shared embedding network to embed into a common representation space. And the output of this model is to determine the engagement and satisfaction of the candidate video for the user after watching the query video. And so engagement include things like whether or not they clicked on the candidate, the served video, whether or not they spent time watching that video. So this is both classification and regression. And the satisfaction correspond to things like clicking like on that video, as well as rating that video, for example. So again, this is both kind of a mixed, discrete, and continuous problem. And then kind of the big question is, how do you figure out the score from these different metrics? And what they do is they actually just use a very simple weighted combination of these predictions, where the weights of those predictions are just manually tuned. And the reason why the motivation that they had here is that the system is very complex itself, and also the metrics for whether or not you're actually serving good videos are online metrics, and they're ones that you cannot that are very difficult to optimize with respect to. And so by doing this in a way that's kind of done manually, it's a bit simpler. It's easier to kind of to iterate on the model, essentially. Okay, so let's talk about the kind of how do we actually predict engagement and satisfaction. So they considered some basic option which corresponds to the multi-head architecture that we talked about before, where you have some shared layers and also some layers that are predicting engagement and satisfaction. This was kind of their baseline, and one of the things that they found is that when the correlation between the tasks is low, that will harm the learning process. As we kind of talked about before, it's sort of negative transfer, right? And so what they did instead is they used a form of soft parameter sharing. And this looked like this, where, and I'll go through the details kind of step by step. So you have some shared bottom layer. And the goal is of kind of this sort of mixture of experts model is to allow different parts of the network to specialize. So you have these different expert neural networks that you want to specialize in different ways. So you can see this example has two different experts. Then you want to decide which expert to use for an input and for a given task K. And so what this corresponds to is you have a different set of weight matrices for each task, and you have an input, and you do a linear combination and a softmax to produce this distribution over which expert to use, and then you compute the features from the selected expert. So you this bottom layer corresponds to, the expert corresponds to fi of x. You then multiply this with the gating function in order to produce the kind of the selected expert output. And then lastly, you compute the output of this. So then you take another neural network H that's going to take the output of the expert and produce the result. So this is an example of an architecture that starts out as shared, branches out into multiple experts, where it may use multiple, it may use just a single expert, and then comes back to a single part of the model. Okay. So in the experiments, the setup here was actually quite interesting. They used TensorFlow and TPUs, as you might expect. They trained in temporal order, where they're feeding in the videos over time, and training continuously to consume the newly arriving data. And they said that this is really important so that because the distribution over time of user engagement is changing as different trends become popular, et cetera. They had various offline and online metrics. For offline, they looked at AUC for classification tasks and squared error metrics for regression tasks. But the most important things were actually the online metrics, because those were actually the ones that you ultimately care about. And so they did A/B testing in comparison to their production system. And the live metrics for this online testing corresponded to things like the time spent on YouTube, survey responses that different users filled out, and the rate of dismissals, which I guess would kind of relate to whether or not they're actually kind of dismissing suggestions or, by the recommender system. And then the last thing worth noting here is that because this is a massive system, computational efficiency also really matters. And so this is one of the reasons why they didn't consider independent training and why they really wanted to do multitask training, such that they didn't have to basically compute everything separately for all of these different metrics. Okay, so here are the results. So the top two rows are showing the baseline network that corresponded to a multi-head network, and the bottom two are corresponding to the mixture of experts architecture. And what we see is that there's a substantial increase in engagement and in satisfaction at around 0.4% and 3% for the larger mixture of experts model, which is nice to see. And also they looked at how different tasks are utilizing the different experts. So each of these bars correspond to a different task. So you can see that expert 7 is typically doing things for task 4 and for task 1, whereas expert 2 is typically computing features for task 2 and for task 3. And then lastly, they found a 20% of this sort of gating polarization where each expert would you would basically actually like not use an expert at all. And what they found is that if they use some sort of dropout such that to prevent it from like only using kind of one expert for all the tasks or not using one expert at all, this was helpful for mitigating that. Okay. Yeah.
Why would you not want to give the model the freedom to use one expert specifically for one task?
Sorry, can you repeat the question?
Like if for example, one task was different than the other one for some reason, wouldn't you want that model to have the freedom to choose one specific expert and train that expert for that
Yeah, so I think that what they mean by polarization here is that they're actually using one expert for all of the tasks, or not using one expert at all. Okay. Let's take a quick, 1 minute break. You guys have been asking a lot of questions, which is awesome. And then we'll try to get into some meta learning. What?
In the early part when they're trying to determine the candidates, they might have used some sort of recommended system. Do they have any way to compare how well this does against some of the recommended systems?
Do you have an example of the other recommender system?
Let's say something like collaborative filtering or something like that. How well do it consider?
I don't have a sense. I didn't in reading the paper. I guess I didn't have a sense for if they did a comparison of this approach versus other things like collaborative filtering. But I guess I would encourage you to take a closer look at the paper to see if they talked about that. Okay, let's get started on the second part. So let's talk about meta learning. We may not have time to get through everything, but if we don't, then I'll cover what we didn't cover at the beginning of lecture on Monday. Okay, so to start off, in many ways, I think that there are kind of two ways to view meta learning algorithms. One is somewhat of a mechanistic view, and another is somewhat of a probabilistic view. So the mechanistic view is a view that I think is very helpful for figuring out how you actually go about implementing one of these algorithms and really understanding kind of the underlying mechanics of how things work and how the implementation works. And the probabilistic view I find to be very helpful for understanding conceptually and intuitively what these algorithms are doing. And so the kind of mechanistic view is that you kind of have this deep neural network that reads in data sets and makes predictions for new data points, such that when you see a new data set, you can make predictions for new data points. And training for this network uses a data set of data sets, each for a different task. And yeah, as I said, this makes it easier to implement meta learning algorithms. Whereas kind of at a high level, the probabilistic view is looking at meta learning as learning priors, essentially learning priors over tasks that in a way that enables kind of combining that prior with a small amount of data for a new task in order to more efficiently learn. Yeah, so kind of learning a task for a new prior uses a small amount of data. And I find that kind of thinking about it from a Bayesian perspective can make it a bit easier to understand what's going on. So I'm going to start with the probabilistic view to give some intuition for what these algorithms are doing, and then I'll go into the more mechanistic view of actually how you implement these algorithms. So for the first part, don't worry about how you would actually go about implementing things. It's more about some of the conceptual aspects of things. So we're going to kind of go back to problem definitions here and kind of redefine things from a Bayesian perspective in order to view meta learning as a Bayesian perspective. So you can view supervised learning as a maximum likelihood problem where you're maximizing the likelihood of your parameters given your data. And in this case, phi is going to be the model parameters, and d is going to be the data set. And of course, kind of as before, the data set contains XY pairs where you have inputs and labels. And you can also view this, kind of redefine it as maximizing the probability of the data given your parameters and maximizing the marginal probability of your parameters. So the first term is your data likelihood, and the second term may be something like a regularizer, like something like weight decay, for example, which corresponds to putting a Gaussian prior on your weights with a fixed variance. Okay, and so then what this looks like is you have some optimization over your data set and given your weights, and then you have your regularizer. Unfortunately, if your data is very large, as we kind of, if your data set is very small, as we talked about, then you might overfit to that data set. And even if you have a regularizer there, it may not be enough to prevent you from overfitting, or it may kind of not be informative enough of actually what you should be learning or kind of the model that you're trying to learn. So the question in meta learning and kind of the key problem that it's trying to answer is when we're solving supervised learning problems, can we incorporate additional data in some way? Like maybe we're not learning from scratch. Maybe we have experience from before that we've we've experienced the world before we're at this point. And that's what's going to be called the meta-training data. We want to be able to use the meta-training data such that when we perform a new task, we can learn it more effectively and more efficiently. And in particular, in meta-learning, this additional data is actually going to correspond to a set of data sets. Basically, a set of tasks or data sets corresponding to tasks. We want to be able to use those data sets such that when we see a data for a new task, we can learn parameters for that task. And then, of course, each of these individual data sets will have k data points. So, for example, if you want to solve a few-shot classification problem, maybe you're given 5 images and you want to be able to classify new images as being among one of those 5 classes. If you try to train a neural network from scratch on this problem, it will either overfit massively, or if your regularizer is too strong, it won't do anything. But if you have data from other image classes, like shown here, then this is your meta-training data, then you might be able to use that meta-training data in a way that allows you to learn from only 5 examples in a manner that is effective. And of course, this doesn't need to be image classification problems. This could be different kind of sinusoid prediction problems. It could be really a variety of other problems that you may want to do, language classification, or kind of, decoding text, for example, etc. Okay, so that's kind of the problem that we want to solve. But what if we don't want to keep around our past experience forever? What if we, if we're going to be training on all of our past experience across tasks, then we don't want to assume that we have to access that every time we want to learn a new task. And so what we're going to do is we're going to try to kind of compile our meta-training data set down to a set of parameters theta, which I'm going to call the meta parameters. And theta is basically going to correspond to whatever we need to know about the meta-training data in order to solve a new task quickly. So basically, if you kind of view if you want to introduce this kind of intermediary variable, if we write out the likelihood of our parameters for our data set, given our past meta-training data, we can write this out in a way that integrates over our meta-parameters theta. So we first infer our meta-parameters theta given our meta-training data, and then we can make predictions of our prediction about our task parameters given our data and our meta-parameters. And note that this assumes that our task-specific parameters and our meta-training data are conditionally independent, conditioned on theta. And we can basically approximate this integral with, this is a fairly crude approximation, but we can approximate this integral with a point estimate for our meta-parameters, where the first, the right-hand side of this is going to correspond to meta-training, where we want to learn a set of meta-parameters given our meta-training data. And the left-hand side of this objective is going to correspond to adaptation, where we want to be able to learn new parameters for a new task, given data from that task and our meta-parameters theta star. Okay, where theta star is equal to basically argmax of log p theta given our meta-training data. Okay, so essentially, this right-hand side is the meta-learning problem, where we're optimizing over our meta-parameters such that when we use them for adaptation, we can effectively learn parameters for that task. Okay, so meta-training is that kind of that second term, and adaptation is is the term now outlined in red. Let's first go over how we can go about adaptation. So we can kind of look at a very simple example, and we'll revisit this example at the end. So say we want to be able to make predictions about test data points. The parameters corresponding to this neural network will correspond to phi star. They'll be the parameters for that task. And we want to be able to infer these parameters from data. So one very simple example for how we might infer these parameters from data is by training a neural network to take in the data set and output phi star for that task. And so where each of these examples correspond to our data set. And so essentially what this would correspond to is we would have kind of these different meta-training data sets. For this data set D, we would pass that into the neural network. We would then give it a new data point, and we want to be able to have it make a prediction for that data point based off of the computed task-specific parameters. So you have this your test input and then your test label. Now, one big question is, okay, we have this is kind of how we're going to do the adaptation process. How do we actually go about meta-training this, this model? So how do we actually basically learn the parameters of our recurrent neural network theta star such that it produces the right task-specific parameters phi star? And so the key idea here is we can basically match test time to training time. So if at test time we're going to be predicting phi star in order to make predictions about test data points, we want to be able to do the same thing at meta-training and basically train this recurrent neural network such that it produces parameters that lead to effective predictions or accurate predictions. So essentially the key idea is that train and test conditions should match. That's basically like the principal rule of meta-learning, basically. If you want to be able to learn at test time, you should basically train it to learn during meta-training. Essentially, you'd be learning how to learn. And then you can kind of view the learning process, the adaptation process as a sort of meta-test time if the forward process is meta-train time. Okay. Right. So the process of optimizing for theta is meta-training. The optimize for producing phi is meta-testing. Now, one of the things that's pretty challenged, if at meta-training time you're actually training it to make predictions about test data points, where do those data points come from? How do we actually optimize for it to make predictions on new data points? And the important thing here is that we need to be able to essentially reserve a test set for each task that we're going to be meta-training over. So if we have a set of tasks and we have basically training data for each task, we also need corresponding test sets for each of those tasks. And these test sets are going to be held out images from those same image categories. Now you might say, okay, now you're going to be training on the test set. This doesn't seem right. That's a good intuition to have. But in this case, we are now moving from training sets to meta-training sets and test sets to meta-test sets. So each of these tasks, the training sets and the test sets for that task correspond to the meta-training data set. And then at meta-test time, we're given new tasks. And we don't want to train on the meta-test set. OK, so we have our meta-training data. This corresponds to training and test sets for every task. Where each of the training set data sets corresponds to k data points. Each of the test data sets correspond to a new set of k data points. Yeah. OK. So the complete kind of optimization problem is that at test time, we're going to be inferring a set of task-specific parameters, which could be some function that takes as input the training data set and outputs the task-specific parameters, where the parameters of that function or the meta-parameters are theta star. And we essentially want to learn a set of meta-parameters such that this function is good for held out data points after getting the training data set as input. OK, so essentially you can view theta star as optimizing this objective where we want to optimize the probability of the parameters being effective at new data points. OK. Cool. So you could also look at this as a graphical model where theta is essentially your prior. Phi I is your task-specific parameters for a given task. And you have a train set and a test set for each task. So phi leads to the data, and theta acts as a prior on the task-specific parameters for all the tasks. Theta is essentially the information that's shared across tasks. OK, and then this dashed line just means that we don't know the kind of test labels for new tasks at meta-test time. But we do know the training data set. OK, some terminology before I get into some of the more mechanistic view of meta-learning. So I talked about this. We're kind of going to call this the meta-training data set. each of these rows is a meta-training task. And each of these tasks has a corresponding train set and test set. The left side of these can be viewed as the training data, and the right side can be viewed as the test data. Another common terminology for this is support set and query set, where you have some set of support images or training images and some query images or test images. And if you have a k-shot learning problem or a few-shot learning problem, k is the number of data points in your training data set. So if you're doing one-shot learning, you're learning from one example. If you're doing k-shot learning, you're learning from k examples. Okay. How does this relate to other problem settings? So multitask learning, like we talked about at the beginning of this lecture, you learn a model with a single set of parameters that solves multiple tasks. And you don't care about generalizing to new tasks. And this essentially can be seen as in somewhat of a special case as meta-learning, where your task-specific parameters and your prior parameters are the same, such that you're just kind of have a single network that is representing all of the tasks. And in many ways, multitask learning is a prerequisite for meta-learning, because if you can't solve the training tasks, then you have no chance of being able to learn new tasks more efficiently than like learning from scratch, for example. It's also related to things like hyperparameter optimization and AutoML. So in hyperparameter optimization, you can essentially view theta as the hyperparameters and phi as the network weights. And in architecture search, you could view theta as the architecture, phi as the network weights. And both of these are kind of very active areas of research and outside of the scope of this class, not this tutorial. Okay, I think we're mostly out of time, and so I will cover the next two parts of the lecture in the next lecture, and we'll probably push back the due date for the homework assignment probably like a couple days, such that you guys have enough time to complete it. Are there any questions about what I covered with meta-learning before we wrap up? Okay, a couple quick reminders before you leave. The homework one is posted today and is not due on Monday, October 7th. Fill out paper preferences by tomorrow, and the TensorFlow review session will also be tomorrow at 4:30 p.m. Bye.